All right. So I suggest that we start. I'd like to welcome you all to this episode of the Distinguished Lecture Series at our institute. Today is a special pleasure to welcome Professor Nergis Mavalvala, who is visiting us from Cambridge in the States. She is professor at MIT, and she just arrived this morning. Nergis originally comes from Pakistan. She did her schooling in Pakistan, and then she moved to the United States for her undergraduate education first at Wellesley College, and then she went to, if I'm not mistaken, then MIT to do her PhD. Already for her PhD work, she was working on developing laser interferometers for gravitational wave detection, and that has kept her in one way or other busy since then. After her PhD at MIT, she went to Caltech for a postdoc, and then later on she joined the faculty at MIT. And she has won a number of awards, as you would expect from someone of her caliber. And we're particularly happy to have found a couple of days in her busy schedule to fly her over to talk to us about her work. And I think in different ways, we are very interested to learn about the new developments. So the floor is yours, please.
Thank you. Right. So, hi everybody. Thank you for that generous introduction. It's a real pleasure to be here. This is the Institute for Light, and there has been sort of perhaps one of the great triumphs of our favorite kind of light, laser light, has been the laser interferometer gravitational wave observatory, or gravitational wave detectors in general. The talk I'm going to give you today is a little bit of something for everyone. So just about a month ago, we celebrated the 10th anniversary of the first direct detection of gravitational waves using these laser interferometers. And so I want to tell you about what's happened. How did we get there to those first discoveries, and what's happened in the 10 years since? And the claim I want to make is that we've opened a new window into the universe. So it's a pretty grand claim, and I hope you'll stay along with me for the journey. So the first thing you want to start with, I'll just sort of fill people in for gravitational waves. So these are ripples of space-time. They were predicted by Einstein in 1916 as part of his theory of general relativity, and this was the dynamical or time-varying part of his metric theory. And he actually, in his original 1916 paper, dismissed them as useless. He said they will never be relevant, and in part it was because he understood how terribly faint they are. Now, fast forward by about 50 years, and in the 1960s, some important things happened. Among them was the first discoveries of neutron stars and black holes. And what that did was it kind of breathed new life into Einstein's original calculations, which were done using ordinary stars. So neutron stars and black holes are sort of the remnants of what ordinary stars like our sun does at the end of their lives, which is they run out of nuclear fuel. The radiation pressure that holds up the star against its own gravity turns off because it's not burning a thermonuclear reaction anymore, and the star collapses on itself. Now, typically, if the star is about 1 solar mass or so, it collapses to a neutron star. But if it's heavier, like 3 to 5 solar masses, it continues to collapse till it collapses to a black hole. And these were discovered in 1967 for neutron stars. And that kind of got this man, Kip Thorne, thinking about what would gravitational waves look like from these kinds of newfound sources. And in fact, what Kip told us was, yeah, they're pretty faint. They'll have an amplitude of 10 to the minus 21. And he told us this in the late 1960s and 1970s. Now, gravitational waves are a strain, so it's a change in length per length. In this case, the length being the region of space-time. And so a part in 10 to the minus 21 would be that for an object of a meter scale like myself, my vertical dimension would change by about 10 to the minus 21 meters. So around the same time, this man, Ray Weiss, was thinking about how we might detect them. And he said, well, they're detectable. We just have to figure out how to be able to measure changes in distance of the order of 10 to the minus 18 meters. And you will notice right away that there's a factor of 1,000 difference between a gravitational wave detector like myself, that's a meter scale, and what Ray Weiss was proposing. So let me take a quick moment to reflect a little bit on that, in particular because this is the 10th anniversary of the discovery of gravitational waves, but it has also just been about a little over a month since Ray Weiss passed away. So what his biggest contributions was he understood that one could measure, remember another important thing that happened in the 1960s was the invention of the laser. So all of this is coming together, and he understood that one could use a laser interferometer to make a precision measurement of the path length changes caused by a gravitational wave. But the important thing was that he understood that it would be completely hopeless to do that on a laboratory scale of a meter scale interferometer. And so he was the first to propose, well, if you really want to do this, you've got to make them long. And he proposed 4-kilometer long gravitational wave detector, and that's where the number 10 to the minus 18 meters, which then became the target for the precision of these instruments for the following decades. Now, Weiss and Thorne met in 1975, somewhat accidentally, and that was when they hatched the plan for a 4-kilometer long gravitational wave detector in the United States, which came to be called LIGO. Not only one, but 2 of them. And then they worked for the next decade and a half through all of the mechanisms of national science funding to get these instruments funded. They were funded in 1989, so 15 years later. They were built through the late 1990s, and then the first versions of LIGO started to operate in the early 2000s. Now, I'm not going to spend a lot of time on how one achieves this 10 to the minus 18 meter target, but I do want to give you a little flavor for it. There are 2 factors of a trillion that you need to achieve. So the first thing is, as many of you know from doing optics experiments, if you just put a mirror and plop it down in a room without any particular protection, and in particular if the mirror is on a flexor or a pendulum, it will move by about a micron. Now, the gravitational wave is going to come by and move these mirrors by 10 to the minus 18 meters. So that's your first factor of a trillion. You have to shield your mirrors from the ambient forces that drive it by a factor of a trillion. And in LIGO, we do it in 2 ways. So let me just go through. You've seen these are the 2 4-kilometer long observatories, one in Washington State, one in Louisiana. And so to get to this 10 to the minus 18 in displacement, we do 2 important things. The first is we use an active vibration isolation stage, very much like noise-canceling headphones. We measure the motion surrounding the platform, and then we feed back. And that gets us down to about 10 to the minus 13 meters. And then what we do is we take the mirrors of LIGO, which are they're 40 kilograms, about 35 centimeters in diameter, and we hang them as pendulums. And we hang them not just from a single pendulum, but from a cascade of 4 pendulums. And what that does is that each layer of the pendulum gives you isolation above its resonant frequency, which is around a hertz. And when you do that cascade of pendula, you can, which is shown here, you can get down to 10 to the minus 18 meters. That's the mirror. That's the actual test mass. There's another mirror above it. Again, these are 2 exquisite pieces of glass to keep the thermal noise low. And then what you see, the other 2 layers of the pendulum are blade springs that are metal springs up here. Okay? Now, you imagine you've succeeded at doing that. You have this super still mirror, shielded from all these external forces. There comes your second factor of a trillion. And the second factor of a trillion is, how do you measure such small motions? So we use laser light. In our case, we use 1064 nanometers, or 1 micron. But we want to resolve 10 to the minus 18 meters. And that's your second factor of a trillion. And what we're really trying to achieve here is that we're trying to make a measurement that's a trillion times smaller than the spacing on the tick marks of our ruler. And the way we do that is essentially by averaging over a large number of photons. And all of you are very, very familiar with shot noise. So we're basically using very high power in our instruments. We start off with a 100 to 200 watt laser. And then in the arms of the LIGO interferometers, we have Fabry-Perot cavities that builds up that laser power to about 750 kilowatts circulating. And then we average over all of that power to bring us down to this trillionth of a fringe. Basically, is the resolution of our measurement. Okay. Once you've done those two things, you might also ask for a third factor of a trillion. Technical, but interestingly, the most expensive factor of a trillion. And that is that to operate these instruments, you need something like 10 to the minus 9 torr. And so that's a factor of a trillion of vacuum below atmosphere. And so even though it's it's a technical, like I said, it's the thing that drives the cost. Okay, so that's what you do. And this was all funded by the National Science Foundation over 4 decades as these observatories came online. And then I'll just draw your attention to this man, Barry Barish. I've already introduced you to Ray Weiss and Kip Thorne. Barry Barish is credited with building the observatories and bringing them into operation. So as I said, they started operating, LIGO started operating in 2000. But before I talk more about LIGO, let me say this has grown into a global network of detectors. There's the two US detectors, LIGO in Washington, Hanford, Washington, and Livingston, Louisiana. There's a 3-kilometer detector called Virgo in Italy. There is a 3-kilometer detector in Japan, Kagra. There is a 4-kilometer replica of LIGO under construction in India. There's also a 600-meter detector just outside of Hanover. And then finally, there is the Space Observatory LISA, which is a 5 million kilometer arm length detector, which has been under development for decades, and it maintains at the moment a 2034 launch date. That has moved by a year every year. So, for the last 20 years. But it's getting built, and there have been fantastic results on Pathfinder missions. So I'm very optimistic it will happen. Okay. Fast forward now to 2015. So the way that LIGO operates is it operated in the first phase called initial LIGO from 2000 to 2010. Lots of technology improvements, but no positive detections, and also lots of upper limits because of seeing no signals, but no detections. And then there was a 5-year break from 2010 to 2015 for a major upgrade called Advanced LIGO. And what that major upgrade means is you basically keep the buildings, you keep the vacuum system, but you take everything else out, all the glass, all the metal, all the vibration isolation, all the optics, all the lasers, and you replace them with better. And then in September 2015, we recorded this signal, which is an iconic, now iconic signal of the first detections of gravitational waves. And there's something amazing in this signal that you just, even if you've seen it many, many times, that's worth reminding you of. So the first thing you'll notice is that the amplitude of the wave, which is the gravitational wave strain, so this is a pair of neutron stars that were orbiting each other, and because they're losing energy to gravitational waves, the orbit shrinks and eventually they collide. And so they've been orbiting each other for 4 billion years, and then in the last 200 milliseconds of their life, we capture their motion in our detector. So at the maximum amplitude here is where the two black holes collide. And notice that the gravitational wave strain amplitude was 10 to the minus 21. So it's a big check mark for Kip Thorne. He told us that this is what we should aim for in 1967 to 69. Okay. If you ask how much were the mirrors of LIGO being displaced when at the moment of this maximum signal, a few times 10 to the minus 18 meters. Big check mark for Ray Weiss. He told us how to do that in 1972. One other thing I'll say is embedded in these bumps and wiggles of the signal is a lot of information about the black holes. From this, you can tell their mass, you can tell their spins, you can tell their distance. And some of these quantities are a little bit degenerate, so you need good signal-to-noise ratio to do it. But that's all encoded in Einstein's equations of general relativity. OK. So this first system was about 30 solar masses each for the two parent black holes. This is something that I never tire of marveling at. At the time that these 30 solar mass black holes collided, they were moving at half the speed of light. Okay? So just try to wrap your head around that. They were about 1.3 billion light years away, and in the collision, about 3 times the mass of our sun was radiated away as gravitational wave energy. Okay? And for this discovery, the founders were given the Nobel Prize in 2017. Now, the thing that I started off to tell you was that we were opening a new window into the universe. And surely you would not be satisfied that a single discovery, however magnificent, opens a new window into the universe. That just gives us a sort of a glimpse of what might be there. So what I want to spend the next few minutes on is what's come next in the 10 years since. So LIGO and its partners, Virgo and Cargra, operate in these chunks called observing runs. The first observing run, we saw 3 events, and that was in 2015. In the second observing run, we saw about twice that. In the observing run 3 and then observing run 4, we've seen many, many more signals. And in fact, by now, we've seen more than 300 gravitational wave events that are confirmed with sufficient signal-to-noise ratio that we can be confident of them. And what you're seeing here is a way of representing them. That's just these time frequency spectrograms, and you can see the characteristic chirp of the in spiral. So far, that's the first thing you want to know. We've seen we've seen only binary in spirals of neutron stars and black holes. Okay? So let me pick out a few of these that I think are interesting science. And then for those of you who are waiting for the light part to come, in the second half of my talk, I'll tell you about the role of quantum light. But in the meantime, I do have to tell you about the astrophysics, because that is the window we have opened. I should have warned those of you who wanted to come halfway in, but I think you'll find this interesting. OK, so this is GW 170817. The numbering is, this is in the year 2017, in the 8th month, on the 17th day. And that was the first time we saw 2 neutron stars colliding. So remember, the first signals were 2 black holes. Now, how can we tell? There's a few telltale things right away. The first thing is the time scale. If you remember, the black hole signals were about 200 milliseconds in our band. Neutron stars, because they're much lighter, they're there for over a second, okay? Or over a minute, rather. So that was the first thing that really made us sit up. 1.7 seconds after we recorded the gravitational wave signal, the Fermi Gamma Ray Observatory saw a very significant trigger. Now, this is important because when black holes orbit each other and collide, unless they're sitting in some kind of environment of gas or dust, there's no light. Black holes in empty space will give off gravitational waves, but no light. Neutron stars, on the other hand, when they collide, this is a giant particle accelerator. You're going to see an incredible and complex shower of light and particles. Okay? And so that was the first thing that excited people, that there was a gamma ray event that seemed to be close in time. Now, when these were detected, it was actually daytime. So they were located. By the way, these gravitational wave observatories locate sources in the sky by triangulation among the observatories. So it was located in the southern hemisphere. And it happened to be daytime in the southern hemisphere. So a big news alert was sent out to the astronomy community. And they had 11 hours to prepare their telescopes to search the patch of sky. And it's a big patch of sky because these gravitational wave detectors without very high signal-to-noise ratio are not very good localizers. So then what followed was a night to remember for astronomers. It was a busy plot. I just want to point out a few fun things for you. So the first thing was that no matter, so this was the gravitational wave signal, here was the gamma ray signal, and then no matter what band you looked in, whether it was X-ray, ultraviolet, optical, infrared, radio, all these different telescopes saw an object. And what did they see? So here's a one that you can focus your eyes. So these are all with different telescopes. The galaxy NGC 4993, and you can see a crosshair for an object in each of these images. So let's just take this one, DLT 40, and look at the same field of view 20 days earlier. Look at the crosshair. There's nothing there. That was a new object that lit up in the sky, and we expect that, because when these neutron stars are just orbiting each other, they're only giving up gravitational waves, but then when they collide, we should expect to see a pretty spectacular light show. And so this is kind of just a fun little thing. These are only gravitation. It's an artist rendition of the two neutron stars. Only gravitational waves are being given off. But then when they collide, you'll see, the first thing you'll see is the gamma ray jets. These are highly beamed. And then you'll see this sort of isotropic radiation of all the particles. And each of these is a different color of light, and the physics is actually, this is called a kilonova, and it had been predicted, actually, the physics of this object about 10 years before we saw it, okay? Now, there's some really spectacular science that came out of this single object. So there's three things that are really fun about it, but I'll tell you about the one that is the most exciting. So it has long been a mystery here on the Earth why we have so much gold or platinum. Now, you might think this is the most absurd statement ever, because entire civilizations have been won and lost over gold. But it turns out, astrophysically, there's an overabundance of these heavy elements. So if you ask, where do the elements of the periodic table come from? They're fused in stars like our sun. So our nearest neighbor star, our sun, can fuse elements up to about iron 56. Anything that's heavier than that, it neither has enough neutrons nor enough energetics to do so. So the next place that you would look for the formation of the elements is supernovae, just like the one I described early on when a star loses its nuclear fuel and explodes. If you look at the energetics in those, you can fuse up to, maybe you can go up to the number of 100. So where do these heavies come from? Gold, platinum, allantonite series, actinide series. So it had been posited that those must come from neutron star collisions, because that's the only environment we know of that's neutron-rich enough to do so. And so here is so let me show you. This is a spectrum. Look at this, is going over days. These are spectra that were taken with the electromagnetic telescopes, and these peaks correspond to the formation of gold. So in that one neutron star collision, we saw something like over 100 Earth masses of gold being formed, okay? And that sort of lays to rest some long-standing mysteries. The first was that we now know, that was also posited, that these neutron star mergers are indeed related to these gamma ray bursts, because remember Fermi saw it. But the thing I wanted to tell you about was this, and take a look at this periodic table. The light gray are primordial, so only hydrogen and helium was made in the early universe. Then the darker gray were all the elements that are made in stellar fusion. And then finally, if you look at the yellows, those are the ones that are formed in merging neutron stars. And we made this table based on the 17 observations. So we now understand to a very great extent where the heavy elements in our periodic table come from. And then one of the things that's really remarkable about that, when you sort of pause and think about it, is that means that sometime in the prehistory of the solar system, a neutron star exploded here. I'm sorry, two neutron stars collided here. And that's a pretty nice thing to imagine as well. All right, so let me tell you about 3 other very intriguing sources. And I want to leave you with the idea that there is some remarkable astrophysics happening with these. So GW 1908-14 is an unusual beast. There's something called the lower mass gap. And that comes about, remember I told you early on, if you're about a solar mass, you become a neutron star. But if you have 3 to 5 solar masses, you become a black hole, you collapse to it. What happens in between? We don't know, because we know that the physics of neutron degeneracy wouldn't allow you to be a neutron star much bigger than 1.5 solar masses. And so here was the first observation of an object. Look at the 2.6 solar mass object that is in between the two. So we didn't know if they could exist. And it seems that they do. Okay? Mystery about how they come about. Another very interesting one is something called the upper mass gap. And so the upper mass gap is something where in the range of something on the order of 70 to 150 solar masses, we also expect there to be no black holes. Why? Because to have stars that massive, when stars that massive, because of electron-positron pair production, you would have a runaway thermonuclear reaction, and it would just explode. It would just blow up. It would not collapse. So again, where do these come from? So that was another interesting mystery. Now, there are, of course, very interesting ideas about that. One could say, for example, well, duh, you see black holes merging, so these merged, and then they found another one, and then those merged, and you have this hierarchical merger. Now, it turns out in the age of the universe, there wouldn't be enough black holes meeting each other to do that in an ordinary galactic environment. So that then gives us some hint that maybe these kinds of heavies are formed in a particularly dense galactic environment, like a globular cluster. But these are the mysteries that are being unraveled by these. And then the last one I'll talk about is one very recent from this year. It's GW 250114, where you can actually start doing black hole physics. And this is my most favorite for a reason that will become apparent in just a few minutes. It's because you can start doing this kind of black hole physics because of spectacular instrument performance. And for those of you who don't know, I love this stuff, but I build instruments. And so that's the joy of this. So with this object, we were able to test 2 ideas that have been out there since the 1950s and 60s again. One is the no-hair theorem, which was given to us by Wheeler and Bekenstein, and that basically says black holes have no hair. Now, what does that mean? That simply means that black holes don't have structure. They are completely described by their mass, their spin, and their charge. 3 quantities, and you're done. And because this was a very high signal-to-noise ratio event, we could actually test the black hole, the no-hair theorem, and it holds. The other thing was something that was given to us by Stephen Hawking, which is called the black hole area theorem. And what that basically says is that the area of a black hole horizon cannot shrink. And the reason for that is that the black hole horizon is actually a measure of entropy. So entropy shouldn't decrease in the system. And we were able to test that as well with 99.9% confidence. Now, why could you do such a thing? Look at this. The upper one was the first black holes we observed. Look at the signal compared to the model. Almost identical systems. Both have about 30 solar masses. Both are about 1 billion light years away. And because the instruments with the improvements are about 3 times as sensitive, you go from a signal to noise of about 25 to over 80. And because you have this high signal to noise, you can start looking for higher order normal modes of the ringing black hole, and that was what allowed us to do these precision tests of general relativity. Okay, so I've set the stage. The instruments are better. What have we been doing? Okay, so part 2 is in improving the detector sensitivity. And so to talk about that, I have to tell you a little bit about what limits these detectors. This is one of my busier slides, but it should be still followable. This is a spectral density of noise that limits our ability to measure gravitational wave strain. And on the horizontal axis is frequency of the gravitational wave we're trying to measure. Initial LIGO, I told you, ran from 2000 to 2010, is the green curve. The red curves were the first observing run of advanced LIGO, where those first signals were detected. And then these other curves are target curves that we've been working towards, and I'll tell you more about what the technologies are. But the thing that you want to notice is this is out of the cumulative detection rate. And you can see in the first two observing runs that it was pretty shallow. We were seeing something on the order of 1 per month. And then we made a couple of significant technology improvements. One of them is the one I'm going to talk to you the most about, which was to use quantum states of light, squeeze states. And we went from about 1 a month to 1 a week, and now we're doing even more than that, of astrophysical detections. You can see the slope just keeps increasing. Okay, so 2 things that I want to point out in this busy plot. So this is a plot that says what are the contributions of instrumental noise to the advanced LIGO sensitivity, which is the black curve. And the only 2 things I want to point out to you are most of the black curve is made up by the purple curve, and that is quantum noise. And that is the quantum optical noise. That is the vacuum fluctuations disturbing our measurement. The other thing you want to pay attention to is the red curve, which is thermal noise of the coatings of our mirrors. And there's no accident that these 2 touch here. The quantum noise at the time was designed to not be better than the coating thermal noise, because that's a lot of effort for being limited by something else. There's one other thing I'll show you on this curve, just because it's interesting for some of you. And that is this thing called the green curve. It's called gravity gradients. It's really Newtonian noise. So what is this? This is the fact that local gravity, local G, fluctuates. Why? Well, a seismic wave goes down below, there's a change in density, and that can move your mirror. If a cloud goes overhead, change in local G, that can move your mirror, okay? And that, it turns out, is indistinguishable from the effects of a gravitational wave. So if you want to measure gravitational waves that are lower in frequency than about 10 hertz, you have to get off the planet. And that motivates LISA. LISA is a low-frequency detector. You can think of it as the radio telescope of optical telescopes that the terrestrial ones are. Okay? All right. So what makes up this quantum noise? This is something very familiar to you all. On the high-frequency end is just shot noise. It's if we use more laser power, we'll make a stronger measurement, we'll pull that down. Okay, so it's the counting statistics of the photons. But then at the lower frequencies here, you have a back action from that. Remember, the mirrors of LIGO are suspended and movable, and the radiation pressure noise kicks the mirror. So you want to use more photons to get a stronger measurement, but then you get a stronger back action from that. Okay? And those are the 2 parts that make up the quantum noise curve. Now, it's a little important to understand where this enters the detector, and so I'll just talk a little bit about squeeze state injection. So let me just say, I told you we went from something like 1 a week to 1 a month, and now even 1 a month to 1 a week, and now even better. About 65, 2/3 of that improvement came from introducing squeeze-like technology into the instrument. And it's very near and dear to me, because it's what my group works on, so I thought I'll tell you about that. I could tell you about the other 1/3, but that's very technical, and this is just what you guys like. So I'll tell you. Okay, so in the early 1980s, Carl Caves already gave us this idea that one should use a squeeze state technique importantly into the unused port of the interferometer. Instead of having an ordinary vacuum state, put in a squeeze state, and you will be able to reduce your photon counting error, or as we call it, shot noise. Okay, so Caves' picture was this. Here is a laser interferometer, and if you arrange these path lengths so that at the output here you have perfect destructive interference, then all of your laser light is going back towards the laser. All of the noise that comes, or the classical noise that comes on the laser light, should go back, but what you still have is an open port here. Vacuum fluctuations enter that open port. And here is a phase space of what that would look like. So X1 and X2 are you can just think of them as they are quadratures. And so whatever field enters here, by the same symmetry of the beam splitter that makes the laser light go back towards the laser, that causes any field entering this port to bounce in the interferometer and come back out this port. Now, if a gravitational wave comes by and differentially displaces these mirrors, a small amount of your coherent laser light comes out, and on that is superposed this vacuum fluctuation. And what Caves told us was, well, that's the origin of your shot noise. And in fact, that's also the origin of the radiation pressure noise, because these same vacuum fluctuations superpose with the very bright field at the mirror and drive the mirror motions. Okay? Caves then told us in that 1981 paper, well, instead of using ordinary vacuum, inject a squeeze vacuum state. Make sure that your squeeze vacuum state is oriented so that the narrowest part of the least noise quadrature is lined up with your signal, and you should do better than just shot noise. Okay? And indeed, that's what we did. So observing run 3, remember, was when we first introduced this. So the busy diagram, you don't need to follow everything. Here is the interferometer. And then here we have, this is the output port where we measure the gravitational wave signal, right here. I'll tell you a funny story of the difference between general relativists and optics people. I was once working in the lab, and Kip Thorne came by. And I was showing him the lab, and I showed him the photodetector. And I said, OK, this is it. This is where we record the signal. And he said, that's just wrong. The test mass is the true detector of general relativity. So for me, test mass is just something that has to be kept still, and it has to transduce signal onto light, and then we measure. For him, that was the object of general. That is the gravitating object, if you will. So, but in any case, this is where we make the measurement. And now what you see is we have added a new piece of technology, which is a squeeze vacuum source. And just for the experts, we use a Chi2 nonlinear optical media. We start off with the same laser that pumps the interferometer. We down-convert it to get a second harmonic, and then we use the second harmonic to pump an optical parametric oscillator. Out of it comes squeezed state. The squeezed state gets injected into the interferometer and then detected. But the more interesting thing here for you all is the results. So the black curve was the sensitivity during observing run 3 of advanced LIGO without squeezing. And then the green curve is what we got when we injected this squeezing. Okay? And as promised, wherever we were limited by, in the bands we were limited by shot noise, we see an improvement. And that indeed gave us a much the increased detection rate. But if you look very carefully, you will see that there is a price being paid. So if you look at this region here, you see that your squeeze curve actually goes above your unsqueezed curve. And that is that radiation pressure back action price that you're paying. What's happening here is that at these frequencies, you're sampling the long part of your ellipse. And that is destroying your ability to measure. Now, for gravitational wave detectors, this is a big problem because we actually collect a lot of information about the gravitational wave source at low frequencies and also at high frequencies. So we really want a broadband detector. So what might we do there? And so first of all, let me just say, so Carl Caves had warned us about this as well. So in his 1980 paper, he wrote, there's been a controversy whether these quantum mechanical radiation pressure fluctuations disturb the measurement. This letter resolves the controversy. They do. So the first thing I want to think of is, OK, that was pretty prescient. He knew it would happen. But the thing that always stands out even more to me is, who gets to write an abstract like this? Like, just come on, just think about this, right? Like, so I encourage you all to try and see what would happen. But anyway, he was right. That's what we saw. And now comes the question of what can we do about it? So that brings me to a third. So Caves gave us those two ideas. And there's a third very important and seminal body of work that came out in 2008 2001 by Kimball and Thorne and colleagues. And that was their ideas for how do you get past this quantum noise limit. Remember I showed you the purple curve and I said quantum noise limit, right? Shot noise, radiation pressure noise. And that became known to us in the late 1990s as we were designing advanced LIGO. And so they gave us some ideas for what to do, and I'll just run you through how we've used their ideas very profitably. So they said you have to, if you want to suppress the standard quantum limit. So let me just tell you first of all what the standard quantum limit is. Let me preface it first by saying that every field has its own favorite standard quantum limit. So that tells you it's not standard. And then as you can see already from this plot, it's not a limit because you can go below it. So even though it's called the standard quantum limit, I call it a benchmark. It's sort of a benchmark. And what is it benchmarking? It's benchmarking this quite fundamental question in our case. It's asking the question, if I use light to probe the position of a particle, how well can I do? Because on the one hand, you want to increase your number of photons to get past the shot noise limit. On the other hand, those increased number of photons give you increased kicks to your particle, the back action. And so this is just a balance between those two. So they gave us three ideas. They said, inject squeeze light. I showed you the result from that. I didn't give you one little caveat, at fixed squeezing angle. Now, what does that mean? When light comes out of my squeeze light source, it's an ellipse, and relative to some quadrature of phase reference, that ellipse is fixed for all frequencies. Okay? So if I did that, you would get this fixed angle squeezed input interferometer, the dashed line. Then they said, well, if you get really clever, try to inject frequency-dependent squeezing. So what's that? That is a squeeze state where the ellipse is rotating as a function of frequency. So at this frequency, it would be maybe pointing horizontal. At this frequency, it could be pointing vertical. And so that was the challenge. How do you make that? And I'll show you what we did. And then they gave us two other ideas that turned out not to be useful because this is only, as soon as you have any optical loss, it's hopeless. And what they did do is they told us that there are optomechanically induced correlations in the interferometer that we should use. So let me just quickly introduce what optomechanical correlations are. So I've told, so optomechanical squeezing. So just think about LIGO or any optomechanics experiment. You can think of it as an optical cavity with a movable mirror. Now, what happens is when this coherent state, the laser beam hits the movable mirror, and it has some fluctuations in its amplitude. Those amplitude fluctuations kick the mirror, the radiation pressure. When the mirror gets kicked, it displaces. When the mirror gets displaced, the reflected light acquires a phase shift, and this is a way in which you can correlate amplitude and phase fluctuation, and that makes a squeeze state. And so in an optomechanical system like this, you're getting a squeeze state. Okay? So what they told us was, well, you're getting this squeezing. Can't you use it profitably? And the problem is that it turns out that the squeezing that's made inside of the LIGO interferometer is exactly the opposite of the one you would want, because it turns out that it has the narrow part of the ellipse the wide part of the ellipse is where your signal is. Okay, so you have to be a little bit more clever than that. And so let me just show you what we end up doing. So what I just want to show you a little piece of data. This is actually true. Here is an experiment we did in our group where we used this kind of optomechanical cavity, except instead of LIGO, this was a micron scale mirror. And instead of using the megawatt in LIGO, we could build this cavity with kilowatts of laser power. And we could show that you get this optomechanical squeezing. So 0 dB is shot noise. And anytime you go below 0 dB, you have a squeeze state. So this optomechanical squeezing is there. We can measure it in these toy systems. And now the question is it really in LIGO as well? And so here is our first set of results. So this was, remember, fixed squeeze angle. And what you can see is that we could indeed arrange our readout quadrature. So the green curve is our data. Now, the thing I should mention here is that the actual quantum noise curve in LIGO is this, the actual noise curve is the gray curve. But based on these shot noise measurements, we know what the quantum noise is, and we can subtract that out. And when we subtract that out, what the underlying quantum noise spectrum is exactly the one that they've predicted for us. And so what we're doing here is we're essentially injecting a squeeze state. And now that squeeze state is interacting optomechanically and getting sheared and rotated because of the optomechanical interaction. Okay? And the combination of those two, if you arrange those two carefully, can give you improved sensitivity. And in fact, there's the standard quantum limit, and we go 3 dB below it. Okay? So that's really nice. As the classical noise improves, we could actually get to this kind of performance, and we're getting there. But it has a problem. And the problem you recognize right away is its narrow band. To make an improvement here at 40 hertz, look at how much we are giving up at other frequencies. Okay? So we don't like that. So then we go to their next idea, which was, well, why don't you put in frequency-dependent squeezing? So what do we have to do to get frequency-dependent squeezing? So here is the blue curve is advanced LIGO without squeezing. The red curve is what we had with squeezing, but at a fixed squeezing angle. So what we have is, if we had a squeeze ellipse that was oriented this way at high frequencies, and a squeeze ellipse that was oriented this way at low frequencies, and everything in between, we could get this. Okay. So now how do we do that? Our squeezers don't know how to do that. Our squeezer gives us a squeeze ellipse that's the same at all frequencies. So now, because you all are here at an Optics and Light Institute, enter a friend that we all know, which is an optical cavity. Now, an optical cavity is an optical resonator, and it has a Lorentzian power profile. Along with that comes a phase shift. Light that reflects off an optical cavity gets a phase shift, and a phase shift for us is a rotation of the squeezing ellipse. So we said, all right, we have to just reflect, and Kimball et al. Told us that we should be done. The problem is the following. The rotation we need to make is at 100 hertz. Why? Because that is the rotation that the 4-kilometer long cavity of the interferometer is making in the first place. We are trying to undo what that cavity is doing. So how do we do that? Well, simple, make another 4-kilometer long cavity. Remember I told you that factor of 1 trillion for vacuum is pretty expensive? So we didn't want to do that. So what we did instead, so what we're really asking for is we want a 100 hertz line with cavity, which LIGO has because it's a 4-kilometer long cavity. So we took the best losses we could achieve and the best finesse we could achieve on this scale, and we instead made a 300-meter cavity. And so enter a 300-meter cavity for LIGO. LIGO now has a little appendage running along one of its arms. And after that, here we go. Black curve is unsqueezed. Green curve is frequency independent. This is what we did for observing run 3. And then purple curve is observing run 4 when we put this frequency dependent squeezing in. And look at the gain right there. Okay? Okay. And then the last thing I'll show you is that indeed, can you go below the standard quantum limit, as in this case with the frequency dependent squeezing? And the answer is yes. We did the same type of measurement now that we have frequency independent squeezing, and we can see this broadband improvement as Kimball et al. Had told us to do, shown us how to do. Okay, and the thing that's beautiful about this, as I already mentioned, is we're doing two things. We're injecting squeezing, and then we're using the optomechanical correlations in the interferometer to shear and rotate that squeezing to our purposes. Okay, I'm going to skip history, even though it's kind of interesting, and there's a story here as well, and just tell you what's going on. Let me just close up with looking to the future. So future detectors are coming online. There is the LIGO replica that's being built in India. There's a site, and construction has begun. At the same time, both in Europe and in the US, designs for third-generation instruments are underway. So in the European version, it's called Einstein Telescope, and the US version is called Cosmic Explorer. And there's one knob that has to be turned to go to these next-generation instruments, and that is length. This is a knob that was fixed in 1970, in the 1970s for the original detector. By the way, if you want to know why it was 4 kilometers, it's also kind of neat. In Europe, it was 3 kilometers because they couldn't find 4 kilometers linear. But in the US, it's 4 kilometers because that's the curvature of the Earth before you have to tunnel. So it was a cost thing. So now there's these proposals. The US one is a 20 or 40 kilometer version. The European is a 10 kilometer version. And then, of course, I told you about LISA, the space detector that is also coming along. So let me finish up by just telling you something spectacularly amazing about these detectors that are coming up. So here is a busy plot, and these are toy curves, but I want to show you what these curves mean. So this was advanced LIGO and observing run 3. This is where we are now. These are some other curves, but take a look at these 3 here. Cosmic Explorer, Einstein Telescope, and Cosmic Explorer has 2 curves because there are 2 phases, imagine. When you achieve these curves here, some remarkable things happen. First of all, each and every one of them assumes these quantum technologies that I already described to you, the squeeze states, the frequency-dependent squeezing. The big challenges now, as you all are painfully familiar with, is controlling the optical losses before you can do better and better. But, these will be deployed in a worldwide network. But the thing that I want to point out is that these curves give us something really spectacular, which is that when you achieve this sensitivity, you will be able to observe black holes, the kinds that we are observing, 10 solar mass black holes, out to a redshift of 10. Now, for those of you who are not familiar with cosmological distances, redshift of 10 is when the first stars in the universe lit up. So what this says is that if you build these instruments, you will see every binary black hole that ever collided. Now, this always blows my mind, because again, who gets to say that? What instrument do we know of that by its, within 2 decades of its first discoveries, or 3, depending on what our government does, can map out the entire population that there is? And there's incredibly other science goals also for these instruments, but that's the one that always really gets to me with cosmology, et cetera. And so I just want to leave you with the notion that we have opened a new window into the universe. We are looking at astrophysics that we've never seen before. We are looking at quantum optics technologies that we've never deployed before. And this promises to be sort of a brilliantly dark and warped future. I want to acknowledge members of all my colleagues at LIGO, Virgo, GEO, and CAGRA, to our funding agencies. And then I'll just leave you with, this is the group of people that I work with on the squeezing experiments. And so, thank you.
Thanks so much, Nergis, for this fantastic talk. It could have gone on for another hour without getting boring.
Thank you. Be careful what you ask for.
There are probably questions. Do we have the cue?
Oh.
Here's your cue.
Oh, thank you for a nice talk. One thing I never quite get about these gravitational wave detections, you have your very long arms, and you measure a tiny change in length in these. Why doesn't this change due to the gravitational wave also happen to your ruler, so to your light?
This is much debated. So there is, as in all field theories, there are different gauges in which you can think about the physics, and the physics should end up being the same. So let me give you a different way of thinking about it, which is how I think about it, and it's very intuitive. So in the end, this L-shaped detector is really for noise reasons, etc. Imagine the simplest thought experiment, which is that I'm a laser and you're a mirror. And I shine my light at you, and it's a pulse, let's say, or it can be CW, it doesn't matter. And I just have a really good clock. You're a good mirror, you reflect back to me, and I have a really good clock. Now, if the gravitational wave comes by, the travel time between us will change. And that, my clock will measure that for the pulse. And then it doesn't matter what the wavelength is, it doesn't matter what the color of the light is, it's a clock measurement. Now, the reason we don't do that measurement is we don't have good enough clocks. We need a clock with a precision of 10 to the minus 31, part in 10 to the 31. We are doing part in 10 to the 21 right now. So that's the reason you have this L-shaped detector. But really, one arm is just acting as the reference for the other arm. And, if you work this out in this so-called transverse traceless gauge as a timing event, the wavelength just falls out. Your ruler falls out.
I think there was another question somewhere in the neighborhood. Stefan, can you get your microphone?
I can also just repeat the questions to keep you all safe.
Yes.
Yeah, thanks a lot. I have a question about your squeezing. You didn't say much about it, but this is not just something I can build quickly in my lab. So this squeezer has some special properties? So
it is actually something that you could build in your labs in about half a year and $500,000. So, but what's special about it? So it is, in our case, so we have a second harmonic generator that is, so we use, quite two nonlinear materials. We either use periodically poled KTP, so PPKTP, or piplin, so periodically poled lithium niobate. And so the big challenges there, so the nonlinear processes are actually quite straightforward. The big challenges are if you want enough of nonlinear gain, you have to carefully engineer your system, you have to phase match. All of our systems are doubly resonant for both colors of light that are propagating so that you get an additional gain. So the complexity of the system is really in the controls and because getting your first bit of green light from second harmonic generation, even my undergraduates in our lab will be able to set something up in a matter of a couple of weeks and do. But then getting it to be, to get what we are seeing. So okay, what's driving the squeezing? So we typically, you can see from my best data, we saw something like 5.8, so 6 dB of squeezing. And that has been heroic, because in our squeezers, on our tabletop, we can make 10, 12 dB of squeezing regularly. But by the time we deliver it to the interferometer, all the optical losses kill us. So remember, the squeeze state is like every other quantum state. It's very fragile. And in our case, you can just think of every loss is a beam splitter that injects ordinary vacuum back in, right? And so that's one challenge, is losses. The other challenge is also quite interesting, which is phase noise. So imagine you make a really, really squeezed ellipse. But then if you have any fluctuations in the squeeze angle, you're seeing this very long part of the ellipse coupling noise into your measurement. And so there's a sweet spot in terms of how much squeezing you can profitably use given how much phase control you have. So there's a whole lot of very technical details, but the principles are straightforward.
And you feed nothing in there, right? You feed vacuum.
Yeah, so that's exactly right. So when the first time I came across, Caves' papers and vacuum, I really scratched my head. But it turns out to be something quite as simple as this is what we do. We set up everything using a coherent field. You get everything locked, you get everything stabilized, and you need other colors of light to stabilize, because what you're going to do to create your vacuum state is after you've set everything up, you're going to block your seed, right? You're going to, and you literally, we put a beam block there, and then you get your vacuum squeezing. And the reason to do that, and this was one of the big breakthroughs when we were struggling with this in the early 2000s, was that even a little bit of coherent field brings an extra noise. And so we work actually very, very hard to be seed-free. So,
thanks a lot.
Yeah.
So my information might be very outdated, but I thought that these squeezing experiments using nonlinearities, they always had a certain bandwidth.
Yes, so they do, and the bandwidth...
At this kind of...
Yeah, so the bandwidth is completely insignificant for these, it's not an issue, because the bandwidth is set by the line width of your OPO cavity, which is megahertz, these are little guys, and the band we're interested in is 10 hertz to 10 kilohertz. So it's completely not. In fact, the opposite was a big challenge for us, again, in the early days, along with what I was saying, which is that if you look at sort of the history of squeezing, I skipped all the history, which is actually quite interesting. Early on, people, because to get squeezing, you squeeze on top of shot noise. And most optical systems are not shot noise limited at 10 hertz. And so there was no one who could produce squeezing at 10 hertz. And so we had to first learn how to do that. And one of the big important breakthroughs to get down to 10 hertz was to be seed-free, because the seed was bringing in all the excess noise. So, yeah.
Wonderful. We have time maybe for one or two questions. There's a question over there.
So thank you very much for the talk. Yeah, I was actually quite surprised when you said like the amount of power going through the interferometer, because for me, I think like when I think of like these very precise measurements, I always think of very, very small amounts of power. So my question is like, so how much power is like circulating in the interferometer, and also if this is in continuous wave operation, so how much do the mirrors heat up? Because I don't know if you have like a ramp up until they thermalize and then they don't shift, or?
All very good questions. So at the final design I showed, we would expect something like 750 kilowatts. At the moment, we're operating around 450 kilowatts. So we're not up at full power yet, for exactly the reasons that you said. So these mirrors are designed to be extremely low absorption, so they're 1 part per million. But you can make the numbers. If you have a megawatt in there and you have a part per million, you have a watt heating your mirror, right? And so what we do is we then actually have a thermal compensation system that heats the mirror from the other side. And we do that with a CO2 laser, and it's designed to be absorptive at CO2. So with 10 watts of CO2, you can undo the curvature change that the absorption did. So if you ask, what's stopping us from more laser power, it's that. It's the thermal load and handling it, and that's been pretty hard. It's also because there's a long thermalization time scale, and the system, the interferometer, is unstable even in that heating up period. So that's the issue.
If I can ask very fast, so what temperature is the operation temperature of the mirrors then?
It's room temperature. Probably heats up by a fraction of a degree or something like that. But yeah, these are all room temperature operation. Now you could ask why not cool your mirrors, especially for the thermal noise problem. And Kagra, for example, the Japanese detector, is a detector that's by design operates cryogenically. In LIGO, we made a very different decision. We actually decided, because to get the most out of cryogenic operation, you want to be operating around 120 or so Kelvin. That's where you have your lowest thermal absorption coefficients, et cetera. But the vibrations associated with that were seen as not worth it. So we are achieving our lower thermal noise by materials engineering, just going to lower dissipation materials.
So you're probably not so sensitive to temperature drifts because you have kind of just change of temperature.
Everything is fed back, and there's over 1,000 feedback loops in these instruments. So yeah, so anything. So I'd say this way: anything we can measure, we're okay with because we can feed back.
Although, okay, so naively you would think that the degree of your feedback should be as good as the degree of your precision, but that's obviously not the case.
No. So again, and in fact, at low frequencies, that again limits you. Your sensor noise that you're putting back into the system can limit you. And if you ask, where, particularly in sort of the 40 to 80 hertz band, we always have some excess noise, and it's mostly to do with noise we're injecting back through our feedback loops, and that's always a work in progress.
All right, I think we have all There's a question in the... do you want to read that? Okay.
Ah.
Do gravitational waves change behavior when observed?
Does their wave function collapse? You know, so I'll tell you, it's actually quite an interesting question because, you know, unlike light, for example, like electromagnetic waves, gravitational waves, matter is quite transparent for gravitational waves. And this has been a double-edged sword for us because on the one hand, it means as a tool for astrophysics, fantastic. It doesn't matter what's between the source and you because the gravitational wave mostly goes right through it. On the other hand, as someone who's trying to build an instrument to detect them, it also interacts very weakly with your detector. But so the answer is inevitably yes, but very little. Yeah, it's not like a photon you've been detected and it's gone. Right.
One last question.
Okay, thank you very much for your talk. I just want to ask, using frequency-dependent squeeze vacuum, the best we can do for the radiation pressure range is to do the same as with on-squeeze vacuum? Like, we cannot get better than that?
Yeah, so I think the question is, can you do any better on the radiation pressure side? So you have, you know, so yes, you can do frequency-dependent squeezing, and that gives you the gains that you do. What limits those gains? What limits those gains is that, remember, the way that we create the frequency dependence is by reflecting it off of a high-finesse optical cavity. And that optical cavity is not lossless. So you actually lose some squeezing due to that. So you could do better with that. And there's another knob you could turn, and that is you just make your mirror heavier. You can say, OK, why don't you just do that? And the problem is that these are the biggest pieces of fused silica we know how to make at the moment of the optical and mechanical quality, so defect-free. Otherwise, the thermal noise goes crazy. So that's the sort of the balance. And then you can say, well, why not just make a composite mirror? Take a mirror and just make it heavier by putting, you know, hanging bricks off it or something. Same thing. It's thermal noise. So anytime you have a material interface, that's a place where you can have dissipation, and dissipation is thermal noise. So.
Great. With that plug for precision measurements, I think we want to thank Nergis again for coming and for giving us this wonderful talk.
Thanks very much.